Hello again. In this video, we're going to go over another related rates problem. So let's look at example 3. It says that coffee is draining out of a canonical filter at a rate of 2.25 cubic inches per minute. If the cone is 5 inches tall and has a radius of 2 inches, how fast is the coffee level dropping when the coffee is 3 inches deep? Okay, so we have a canonical filter. In other words, it's cone-shaped. The cone is 5 inches tall and it has a radius of 2 inches. Now inside this filter, we have some coffee. Now the height of the coffee, which is a variable, we're going to call h. That's the distance from the bottom of the filter up to the top of the coffee level. And of course, it's a function of time, because as time evolves, the height of the coffee level is dropping. Another variable we have in this problem is the radius of this little circular part at the top of the coffee. Of course, that's a function of time as well, because as time evolves, this radius is going to decrease as well. Okay, so h stands for the height of the coffee in the filter, then r stands for the radius of this little circular piece at the top of the coffee level. Okay, and then we can find the volume of this coffee inside the filter. Since it's cone-shaped, the volume should be 1/3 pi r squared times h. That gives you the volume of coffee inside the filter. That's just coming from the volume of a cone. Okay, now let's look at the rates of change that were given in this problem and the rate of change that we're looking for. So if you read here at the very first sentence, it tells us that the coffee here is draining out of the bottom of the filter at a rate of 2.25 cubic inches per minute. So that's a rate of change in the volume over time. So that's a derivative, right? It's dV dt. But it's negative because we're losing volume inside this coffee inside this filter. We're losing volume in here because it's dripping out of the filter. So the dV dt is actually negative 2.25 cubic inches per minute. And then the rate of change that we're trying to find is we want to know how fast the coffee level is dropping when the coffee is 3 inches deep. In other words, what's the rate of change in the height over time? So dh dt, right when h is equal to 3. So the height here is equal to 3 inches. Okay, so we're trying to find dh dt right when h is equal to 3. Okay, so here's how we're going to do this. We have two rates of change that we need to relate to each other. We have dV dt, which we're given. We're trying to find dh dt. Now remember, you need to start with a foundational equation. So we need to relate volume to height. And once we have volume related to height, we can take the derivative of both sides with respect to time, and then we can relate dV dt to dh dt. And we almost have that. Here we have volume in terms of radius and height. So if we can just substitute for the radius and have it be a function of just height, then we can take the derivative of both sides of this equation with respect to time and relate dV dt to dh dt. Now here's how we're going to do that. Notice in this problem we have two similar triangles. So if you look at this triangle right here, this larger triangle, of course this is 2 inches because that's the radius of the cone. And then this distance here is 5 inches because that's the height of the cone. So that's our bigger triangle. And notice that's a right triangle. Okay, then we also have this smaller triangle, which looks like this. But these are variables. So we have this radius of the coffee level at the top, which is circular. That's a variable, r. And then we also have this height, the height of the coffee level. That's also a variable that changes over time. Okay, and so we have this second triangle. They're similar triangles, right? This larger triangle and the smaller triangle are similar triangles. And so we know that when we have similar triangles, ratio of one side to another side for one of the triangles, so R over H, is the same as 2 over 5 for the larger triangle. So if you take one side of this triangle and divide it by this other side, that ratio is the same as taking this side and dividing it by this side. So we know R divided by H is the same as 2 divided by 5 because they're similar triangles. And what that's going to allow us to do is we can now solve for R and substitute that R into this equation, and then we'll have everything in terms of H. Okay, so let's go ahead and do that. Okay, so let's take, we know R divided by H is the same as 2/5 because those are similar triangles. And if we solve for R here, just multiply H to the other side. So we get 2/5 H, and then we're going to substitute that in for this R here. Okay, so this is 2/5 H for R, and then that's going to get squared. So let's square that out. So when you square this, you just get 4 over 25 times H squared, and then times this H. Of course, that's going to give us H cubed. We also have a pi in here. And then that gives us H cubed. And over here, we're just going to get 4 pi all over 75. Okay, now we have volume in terms of height, which is exactly what we need, because now we can take the derivative of both sides of this equation with respect to time, and we can relate these two rates, dv dt and dh dt. Okay, so let's do that. Take the derivative of both sides with respect to time. Of course, this is a constant, so that can come outside the derivative operator. Now, when we take the derivative of this, we're going to have to use the chain rule because h is really a function of time, and we don't know exactly what it's equal to in terms of t, but we do know it depends on time. So you need to view this as an inner function that can be written in terms of t, even though we don't know what it's exactly equal to. Okay, so that's our inner function, and then it's being cubed, and that's our outer function. Okay, so we're going to have to use the chain rule to find that derivative. Okay, so the outer derivative is just going to be 3h squared, because the 3 comes down and you subtract 1 from that exponent. And of course the inner derivative is just going to be the derivative of h, which is the inner function, with respect to time. So we get dh dt. Okay, so that's just the chain rule. The outer derivative here times the inner derivative. Okay, and that gets multiplied by the constant. And now we have a relationship between two rates of change. dv dt is being related to dh dt now. So that's why this is called a related rates problem. Okay, so now let's solve for dh dt right when h is equal to 3. Okay, I'm going to go ahead and multiply this 3 by the 4, so we get 12 pi all over 75. And then h squared. Of course, h, we're evaluating this when h is equal to 3, so that's going to be 3. And then dh dt is being evaluated at h is equal to 3, as well as dv dt. Right? Everything is being evaluated when h is equal to 3 here. Now, dv dt is a constant. It's always negative 2.25 cubic inches per minute. So when h is equal to 3, it's still negative 2.25 cubic inches per minute because it's constant. So we know what this number is. Okay, and this is equal to 9. 9 times 12 is 108. So we get 108 pi divided by 75. And then dh dt, right when h is equal to 3, that's the thing we're trying to solve for, right? That's the rate of change we're looking for. Okay, and now just to finish this off, we just need to divide this to the other side, or you can multiply by its reciprocal, which is 75 over 108 pi. And that's going to leave us with dh dt when h is equal to 3. Okay, so you can plug this into your calculator, and you end up with negative 0.497. And then let's go ahead and put the units back in here. You can see what the units are going to be. This is the height over time. The height is being measured in inches, and time is being measured in minutes. So this should be inches per minute. Okay, so let's go back and just kind of think about what this is telling us. This is approximately, let's just think of this as about 0.5 inches per minute. Okay, it's losing a height of 0.5 inches, half an inch per minute. Let's go back and look at the diagram. So what's happening here is coffee, of course, is draining out the bottom of this filter at a rate of 2.25 cubic inches every minute. That's how much volume it's losing every minute. Okay, as that happens, though, the height of the coffee is of course going down. The height of the coffee level is going down. And the rate at which it's going down, h dt, right when h is 3 inches, right, which is somewhere in here, because this is 5 inches, the rate at which the height is dropping with respect to time, right when h is equal to 3, is about half an inch every minute. Okay, that's the rate of change in the height with respect to time, right when h is equal to 3 inches. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.